Hello, this is Sean Mullery from Electronic Engineering at IT Sligo, and what I'm going to cover in this short video is the compile process. Now, I've mentioned in a previous video that there is more than one use for the term compile. Some people refer to the compile process or the compiler as the overall build process, the bit that does all your development, all your debugging, and all your creating of the machine code. But that there is another use of the word compiler, and that's the very specific part of actually compiling part of the code. It's a much smaller part of the overall process, and that's what I'm going to explain here. The three things that I'm going to mention are the preprocessor, the first pass, and the second pass. Now, these are kind of generic terms that are used within the compile process, but it's important to realize that different compiler makers do their compile process in slightly different ways, and as well as that, a lot of the terms here are often used in different ways as well. So sometimes people include the preprocessor as part of the first pass. The second pass might be something slightly different from what I show here. So it's not too important that you remember that the first pass is this and the second pass is this and so on. What I really want you to get from this is the overall set of steps that have to be gone through in order to actually compile the program. And bear in mind that the output of this will not actually be the final executable or the machine code. It's actually only a small part of that process. There are other bits that we have to do as well. We'll be doing those in another video. So to explain the preprocessor first, and this is really considered separate from the compile process because it's a little process of its own. And what it does is it scans the C file and it scans each individual C file. So it deals with each C file individually, not them all together. So it scans the C file and produces a new pre-processed file that contains the original C code, but it also replaces sections of the code with patterns that the programmer has defined. I'll give an example here of a hash define where I've said pi, so capital P-I, and that's obviously for the number pi. And what I want as a text substitution there is the number 3.14159. And of course I could give it more digits as well, but we'll stop at that. Now, anywhere that pi is used in the C code, it will be replaced with 3.14159. So that'll be directly pasted in there in its place. So pi will no longer appear in the pre-processed file. What will appear is the actual number 3.14159. Just as importantly, though, as well, what the preprocessor does is that it takes whatever header files you have at the top of the file. So you'll be used to, from C programming, putting in things like stdio.h and so on. It takes those header files, the entire contents of them, and pastes them at the beginning of the preprocessed file. So in actual fact, you'll find that your preprocessed file, a huge amount of it is taken up with the text from those header files, and then only maybe a small amount at the bottom, depending on how much C code you've written, is the actual C code from that file. And bear in mind, this is all done on a file-by-file basis, so if you have more than one file, you'll have more than one source file or more than one C file, you'll have more than one pre-processed file as well. The first pass, this is sometimes called parsing. And what it does is it breaks up the code into small little elements or tokens. And again, there are lots of different terms that are used here for this, but it's basically breaking it down into small little sections that are manageable for it. It then organizes them into a structure called a tree. So it can go back to that structure later and try and turn that into machine code or assembly language, depending on which your compiler system wants to do. If it notices anything that's obviously incorrect as it's doing this breakup of the code, in other words, if it's trying to break the thing up and it's saying, well, actually, I don't know what to do here, I'm not sure where to stop. This often happens like if there's a semicolon missing or something and it knows that something's wrong, it can't properly construct the tree, it'll generate an error. So those are the errors that you're used to seeing when you run a program and you've made a mistake in it somewhere, like you've forgotten a semicolon, or you've done some other thing, like you've forgotten a bracket somewhere or a closing brace, any of those things that you might do wrong. It can't construct its tree properly, and it knows something's wrong, and it tries to point out to you roughly where it is. As we've seen before, it doesn't always get it right. It sometimes ends up on the line afterwards because that's where it comes across the problem. So these could be your basic syntax errors, or it could be where the compiler does not recognize a variable. So oftentimes what happens is people use a variable name and they haven't declared it at the top. So, so if you have int I up the top, then you can use the I variable later on down below. But if you just use I in the middle of your program and you haven't said int I up the top, because this passes through it in a very linear fashion from top to bottom, if it hasn't come across the variable before, it doesn't recognize it and it doesn't know what to do. Again, it can't construct its tree in order to do it. The other thing that could happen is you could have a function such as the printf function, and you may be using it incorrectly. So you might have called it the right name, the printf name, but you might be using it incorrectly. Or it could be one of your own functions that you're using incorrectly again. So in other words, that it's expecting an integer and you haven't passed it anything. Okay, so those are examples where it realizes that you have not used the thing correctly in order to actually write it. Okay, so again, that might throw an error, and that would normally happen kind of on the first pass, depending on how the compiler is actually implemented. Now, the second pass, then, this is sometimes called the code generator, because what it does is once the tree is fully constructed and that's all okay, it goes through the tree and it creates either assembly language instructions or machine code directly for each part of the tree, so that it can actually construct the machine code. Sometimes it does an intermediate one where it does it into assembly first. That's particularly useful if you want to link it up with other assembly files later on. From this, from turning it into that, it creates an object file. Okay, they're known as object files, or sometimes .obj, but they also have other extensions on them depending on what compiler system you're using. But it's important to realize this is not the final executable. It's not the final hex file or the .exe file, depending on what system you're on. Sometimes the second pass also attempts some optimizations, and this is where it thinks that it can do thing a little bit more efficiently than you have written it. Okay, this can be both a good and a bad thing, because sometimes it tries to do something that you didn't want it to do. It creates an optimization you didn't want. Sometimes, most of the time, it actually creates an optimization that makes your code either run faster or that fits your code in a smaller amount of space, both of which are very useful things to do. It's usually best, though, if you can anticipate the optimum way to actually write your program. If you can anticipate that, then you can either write the program with that in mind, so that it forces that optimization to happen. In other words, that you're not relying on the compiler to make that optimization. Or if it's something that you don't want to happen, then you write your program to make sure the compiler knows, don't optimize this. This is exactly how I want it to do. I won't say any more on that for the moment, because we'll be seeing examples of that throughout the course, so I don't want to burden you with too much detail at the moment. Now, what I want to do at this point is I just want to open up the MPLAB-X system here. And what you can see is I've got a number of source files, and again, we'll be going through more detail on how to set these up, so don't worry too much about them at the moment. But you can see there are actually 5 source files there: configurationbits.c, interrupts.c, main.c, system.c, and user.c. I'm only going to look at main for the moment. What I've done here, I didn't really need to do it, but I added it in anyway, is I made a hash define that I called max, M-A-X, and I set that to 32. And what I did then later on in the code is that I said if count is equal to max. Okay. Now what will happen is that when we run when the preprocessor runs on this, it'll change that max into 32, and we'll see that. The other thing as well is that there are a number of header files mentioned up the top here. There's xc.h, but in actual fact what that does is it generally goes and finds the particular chip that we wanted, and it actually adds in the appropriate header file for us, but it also adds in these other ones as well. So what I'm just going to do here is I'm just going to move to not to that one, no, just to here. And again, I'll be going through a little bit of this with you later, so you don't need to remember where this is, but there are a number of .pre or pre files that are created here. These are the preprocessor files. So these are the files that are created after the preprocessor. I can open it up there and take a look at it. And what we notice here up the top is that we've included a header file called pic16f88.h. That happened to be the particular chip that I was writing the program for. And it's basically taken everything from in that header file and pasted it in here, and it goes on and on and on. I mean, we could scroll down here for a long time. If you notice the scroll bar on the right hand side, you can see that we have quite a bit to go before we get to the bottom. So to speed that up, what I'm going to do is I'm going to go right to the bottom, Just show you the last few. We have another head file here called standard bool, and there was one above that called standard int, and a few of those. So it's pasted all the information from those in as well. But down the very bottom we have our actual main.c file, and we can see that it's put in all the C code, but the one difference we should note is that down here it now says if count is equal to 32. So it's removed the max and put in the 32 in its place, and that's part of what the preprocessor does. So this is before it actually starts to compile the program. This is literally just pre-processing so that it's ready to run. Of course, it's not as nice to read the preprocessed file because it's not properly indented or anything. It's not really meant for a human to read it, but it's very useful for the computer as part of the process. Okay, just a final few things to mention on this whole process here. Because what we'll be doing in one of the next videos is we'll be talking about what happens after this point. So I said that this creates an object file. What's important to realize is that, let's say, for example, if you think back to standard C when you used to use the printf function from stdio.h. Now the preprocessor would have pasted all of stdio.h in there, and during your first pass it would have checked whether you were using the printf function correctly. In other words, you were doing it as the header file, the stdio.h file, said it should be used. What's important to realize though at that stage is that it hasn't actually implemented the code that actually writes the thing to the screen. That happens later in the process. So you have an object file there that relies on other object files and other libraries in order to run that part of the code. So this is important when you run the compile process, what we strictly call the smaller version of the term compile process. All we're doing is we're dealing with individual files at that stage and checking if they're correct in syntax, correct in the way we've called functions, and later on then it's part of another process to actually link all those together. And in fact that process is called linking, so it's very appropriately named. So we'll be coming to that in the next video.